So, let us take another example. Okay, we have so far considered an AND gate. Okay, and we said that we looked at every possible fault. We can have A0, A1, B0, B1, C0, C1. These are the possible faults. And yesterday we tried and argued what are the test vectors required to test for each of these faults. See, for example, A0. Okay, a good circuit will produce a 1. I am sorry, a good circuit will produce a good circuit will produce a 1 when A is stuck at 0 and we apply, let us say 1 1. Okay, a faulty circuit will produce a 0. Okay, so 1 1 is a test vector. Okay, so you can verify. If I apply 1 1, a good circuit will produce a 0, but a faulty circuit will produce a 1. Similarly, suppose we had A stuck at 1, then if I apply a 0, okay, and a 1, a good circuit will produce a 1, but if this was stuck at 1, a bad circuit will produce a 0. Okay. So, remember this notation. This is what the good circuit has and this is what the faulty circuit has. So, if A is stuck at 1, a faulty circuit will have a 1 here, and as a result it will produce a 1, whereas a good circuit will produce a good circuit will produce a 1, a faulty circuit will produce a 0. Okay. So, I think I made a mistake here. Here both will be 1, the good circuit as well as the faulty circuit will have a 1. So, similarly B0, if you apply a 1 1, a faulty circuit will have a 0 and a good circuit will produce a 0, but the faulty circuit will produce a 1. Okay. So, let us write down A1 is 0 1, B0 is 1 0, I am sorry, B0 is also 1 1. B1 so we have to apply a 0 here and a 1 here. So, a good circuit will produce a 1, a faulty circuit will produce a 0. So, a 1 0 is a test vector for this. C0, so we want the faulty circuit to produce a 0, but a good circuit to produce a 1. Okay. So, we have several choices. We can apply either 0 0 or 0 1 or 1 0 0. All three are okay. They will all produce so if I apply 0 1, both the good and the faulty circuit will have a 0 1. Good circuit will produce a 1, but a faulty circuit will produce a 0. So, here the C0 is what we are looking at. Okay. Here it was B1, right. Then last but not the least, we have we have C stuck at 1. That means the output should be, good circuit should produce a 0, but faulty circuit will produce a 1. So, here the test is 1 1. So, a good circuit will produce a 0, but a faulty circuit will produce a 1 because there is a stuck at fault at the C. Okay, so this is 1. So, if I start picking the vectors, see, suppose I pick vector 1 1, okay, that catches A0 and it also catches B0. If I look at 0 1, that catches A1 and C0. Okay. If I look at 1 0, that catches B1 and it catches C0. Okay. Then finally 0 0, okay, that catches C0. Okay. So, you can pick the test vectors. I hope you will realize that all 4 vectors are not required. Okay. We can pick A1, that will take care of A0 and B0. Then if you pick A0, it will take care of A1 and C0. So, C0 is already gone. C0 is already gone. We have to only now worry about B1. B1 can be tested using 1. So, these are the required test vectors. So, 3 out of 4 vectors are required. Okay. All right. So, as an exercise, I want you to try a NOR gate. Okay. Try a NOR gate. The test vectors for a NOR gate is what I want you to find out. Start with the fault list A0, B0, A1, B1, C0, C1, and try to find a test vector for each of these faults, okay, and then construct a table like the one which we did before. Okay, what does A1, what does the vector 1 1 catch, what does the vector 0 1 catch, etc., etc., and then pick the minimum number of test vectors required, right, and you can try the same thing for and or. So, this is an exercise. Find the minimum number of tests in each case to catch all faults, all single circuit faults. So, you have to find, okay, you will find that it is very similar, okay, whatever we did earlier. Okay. So, please try this exercise. Okay. Now, let us look at the same NAND gate. Okay. So, sometimes we use this notation. This dot is used to indicate a stuck at 0 fault, and circle is used to indicate a stuck at 1 fault. So, stuck at 0, stuck at 1, stuck at 0, stuck at 1. Okay. A0, A1, B0, B1, C0, C1. These are our faults. There are single stuck. These are the 6 single stuck faults at the input and output of a NAND gate, and we have represented them like this. Okay. Now, let us look at A0. Okay. That means this wire is stuck at 0, and a result of that is C becomes 1. I am sorry, C becomes C becomes 1. So, if A is stuck at 0, C will become 1, and if so the effect of A stuck at 0 is C becomes 1. You will realize that the effect of B0 is also the same, and the effect of C1 is also the same. So, in a way these are all equivalent, we cannot distinguish between them. When these faults occur, the output is 1. So, if I take this NAND gate, okay, and if I try to find a test vector for A0, okay, a stuck at fault here will cause a 1 here, but a good circuit will produce a 1, right. But B stuck at 0 will also do the same thing. A stuck at 0 will also produce a 1, and C stuck at 1 will also produce a 1. Okay. So, we cannot distinguish between A0, B0 and C1. So, they are all equivalent. Okay. So, we can go ahead and say, look, I am not really going to test for all of them. It is enough to look for A stuck at 0 and then C stuck at C stuck at 1. So, we have eliminated B stuck at 0, and we have eliminated C stuck at so, the advantage of equivalent fault is that it is enough to consider one of them. It is enough to consider one of the 3 equivalent faults. So, either consider A0 or consider B0 or consider C. There is no need for you to separately generate a test vector for A0 and B0 and C1. In fact, they will be the same. You already saw that, right. We already saw that for A0 the vector is 1 1, for C0 also it is 1 1, and for B0 also it is 1 1. Okay. So, this is a way we can reduce our work. Okay. We do not need to consider all the faults in the circuit, we can consider only some of them. Okay. So, in the same way I wanted to argue about, let us say, an OR gate. So, we have the stuck at 0, stuck at 1, stuck at 0, stuck at 1, stuck at 0, stuck at 1. You will appreciate that this A1 is equivalent to B1, right. If A is stuck at 1, the output is 1. If B is stuck at 1, the output is 1. Similarly, if output C is stuck at 1, the output is 1. So, there is no need to test for all the faults. So, we can eliminate, we can retain A1, we can eliminate B1 and we can eliminate C1. Okay. So, we have 4 faults. I think in the previous example, I think I missed one. See here, I still need to do A0 and A1. A0, A1, then B1 and C0. Okay. So, we have reduced it to 4 faults. So, from 6 we have brought it down to 4. Here also from 6 we have brought it down to 4. Okay. So, using equivalence we can reduce the number of faults. So, using fault equivalence, we can reduce the size of fault list. So, from 6 faults we have brought it down to 4 faults. Let us do a little bit more, right. Remember, let us take this OR gate. So, we are left with A0, A1 and B1 and C1. So, let us write down the test vector for A0. So, for A0 testing, a good circuit will produce A plus B, whereas a faulty circuit will produce B. So, we have to somehow make sure that these are different. So, by selecting both let us say 0 0, I am sorry 1 0. So, if I apply 1 0, 1 plus 0 is 1, whereas here B is 0. Okay. So, 1 0 is a test vector, right. So, if I apply 1 here and a 0 here, a good circuit will produce a 1, but if this guy is stuck at 0, it will have a 0, and as a result this will also produce a 0. Similarly, A1, so a good circuit will produce an A plus B, whereas a faulty circuit will produce a 1, right. So, we have to apply A and B such that we get a 0 here. So, this is a 0 0. So, if I apply a 0 0, a good circuit will produce a 0, but faulty circuit will produce a 1. Similarly, B1, a good circuit will produce a plus B, but a faulty circuit will produce a 1. So, you must select A and B to be 0 So that so this is also 0 0. So here a plus b and c 0, right, c 0, output is 0. A faulty circuit will produce a 0, a good circuit will produce a plus b. So if you want the good circuit to produce a different value than 0, we have three choices. We can do 0 1 or 1 0 or 1 1. So here I am sorry. So it can be 0 1 or 1 0 or 1 1. This is C 0, that was a mistake. This should be C 0. Okay. See, the observation that we have to make is that C 0, right, we can eliminate it because a subset of this, see, these are the test vectors which detect C 0. Okay. So, there are three vectors 0 1, 1 0 and 1 1 that detect C 0, right, and it so happens that A 0 contains that 1 0, which is a subset. So, if you detect for A 0, okay, if you detect A 0 with a particular test vector 1 0, it will also detect C 0. So, there is no need to keep C 0 at all. Okay. So, in other words, suppose this is a set of vectors which catch a fault f, and let us say here is another fault g. Okay. So, this is a set of vectors which catch fault g. So, what it means is if I pick a test from here, it will catch both of them. So, any test for f is also going to cause catch g. So, there is no need to separately test for g. So, we say g dominates. So, it is a dominant fault, and as a result we eliminate that fault. Okay. So, remove g. I hope this is clear, right. So, in this example C 0 is a dominant fault, that means the test vectors for C 0 contain the test vectors for A 0. So, we can eliminate this also. So, with the help of equivalence we were able to bring it down to 4 faults. With the help of your dominance we can eliminate this also. So, now we have been able to reduce to 3 faults. So, originally 6 faults, now only 3. So, 50% reduction. Okay. Earlier we were able to get from 6 to 4 using equivalence. Okay. So, using equivalence, okay, whereas using dominance and equivalence, we are able to reduce the number of faults to, okay. Good. So, let us look at a slightly bigger circuit. And we can start with the complete set, 1 stuck at 1, 0 stuck at 1, stuck at 0, 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 stuck at 1. Then we can go ahead and argue as to what is equivalent, etc. See, A0 and B0 are equivalent because it is an AND gate. So, if A is stuck at 0, E will become 0. If B is stuck at 0 also, E will become 0. Okay. So, there is no way to distinguish these A0 and B0, and in the same way there is no way to distinguish A0 and E0. So, we can go ahead and eliminate, right. A0 will keep, will remove B0, will retain B1 and will retain this guy. Similarly, we can retain this and we have already argued that in an AND gate, okay, we can eliminate using equivalence, we can eliminate E0 and similarly we can eliminate F0, okay, and then these two are still there. Okay. You can continue to use dominance and see whether we can eliminate more. Okay, as of now we have only looked at okay, wait a minute, we have not yet looked at stuck at 1, etc., right. So, this stuck at one of them can be removed. So, we can remove this guy and we can remove this guy. Okay. So, we have reduced, originally we had how many, 1, 2, 3, 4, 5, 6, 7, 14 faults. With only equivalence, we were able to reduce 3 plus 3 is 6, 8, 9 and 10. We eliminated 4. We may be able to eliminate more, okay, using dominance. Okay. So, we can try that dominance method. What does it say? If we find the set of all test vectors for, let us say, this guy over here, C0, I am sorry, G0, G1. Okay. So, find the set of all vectors for G1. Okay. Let us do that. So, what is it? What is the good circuit behavior? AB plus CD. Faulty circuit is it will produce a 1. Okay. Now, our test that technique that we discussed earlier, it says that the good and the faulty circuit must produce different output. So, AB plus CD XORed with 1 should be 1, or AB plus CD should be equal to 0. As long as AB plus CD equal to 0, we have detected this fault. And you will realize that there are many ways to do this, right. We can try A equal to 0, C equal to 0, that will work. A will become 0 and CD will also become 0. We can try B equal to 0 and C equal to 0, that will also cause. Then we can try A equal to 0 and D equal to 0, that will also cause this. And then finally B equal to 0 and D equal to. So, there are 4 test vectors. Okay. So, 0, so A is 0, B is not important. So, we can say X, C is 0, D is X. So, 0x means A is 0, B is unknown or rather do not care, C is 0 and D is do not care. We can also have B 0 and C 0 and these are do not care. We can have A 0, D 0 and these are do not care, or we can have B 0 and D 0 and these are do not care. So, we have quite a few test vectors for output stuck at 1. So, G1, the vectors are 0 0 0 0 or 0 1 0 0 or 0 0 0 1 or 0 1 0 1. Similarly, we can have 0 0 0 0 is already taken. We can have 0 0 0 1, that is also already done. So, we can have 1 0 0 0 and 1 0 0 1, and similarly we can have 0 1 1 0, 0 0 1 0, 0 1 0 0. Okay. These are also vectors because of this, and 1 0 1 0 and okay. So, I can think of 1 2 3 4 5 6 7 8 9 10 vectors. Okay. Now, if you work backwards and see what tests E1 is going to come. Okay. Let us look at E1. So, E1, a good circuit will produce AB plus CD, a faulty circuit will produce a 1. So, once again AB plus C, oops, sorry. So, AB plus CD must be 0. Okay. So, test vectors for E1, okay. No, I think I made a mistake. Sorry, it's my mistake. See, when E1 is present in the circuit, the faulty circuit produces CD. Okay. A good circuit produces AB plus CD. No, this is correct. This is correct. When E1 is present, 1 is getting it. Sorry, this is correct. Okay. So, we have to apply AB plus CD to be equal to 0. Okay. So, we will realize that we may end up with the same vectors, okay, because here also the condition for, so AB plus CD equal to 1, here also AB plus CD equal to 1. So, in other words, G1 and E1 may have identical sets of test vectors. So, one of them can be eliminated. So, there is no need to separately test for, let us say, this G1. Okay. So, using dominance and equivalence, right, you can further compact the list of faults. So, this is, some people like to call it as fault compaction. So, the list of faults gets compressed. This is important because, see, when you have a very weak circuit, right, imagine that there are millions of gates, right. So, you have a huge list of faults, and if you can use equivalence and dominance to sort of cut down the total number of faults, that reduces the effort involved in testing. Okay. So, that is the basic reason why we do fault compaction. Okay. Let me take one more example. Okay. See, this circuit is slightly different from the previous circuit that I have discussed, because it has got what are called as fan out. So, there is a branching that is happening. Okay. So, this is known as a fan out stem, okay, and these are called the fan out branches. Okay. So, if you look at the total number of faults, you have to start with stuck at 0, stuck at 1, 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 stuck at 0, stuck at 1. So, there are many faults. Okay. Let us call this guy E. We can call this E1 and E2, and oh, I already called this E. Okay, let me just change this. I have already called this E. So, let me call this H or something like that, and let me call this H1 and H2. Okay. So, our list of faults will unfortunately have A0, A1, B0, B1, C0, C1, H0, H1, H1 0, H1 1, H2 0, H2 1, right. And then E0, E1, right, F0, F1, and then finally G0, G1. This is without any compaction. Then we can start compacting. We can say, look, A1 and H11 are same. Okay. So, the stuck at 1 and stuck at 1 here cannot be distinguished. Similarly, H21 and D1 are same. E0 and F0 are same, they are equivalent. E0 and G0 are same, they can, so we can start eliminating based on equivalence. Okay. So, we start with equivalence and then we look at how we can use dominance, etc. Before we get to that, let us argue why H1 and H2 are different. Okay. If I have a standout branch like this, we consider them to be different. Okay. Sometimes people ask me why. Okay. See, it is possible that there is a wire, this may have become open circuited, but there is no problem here. So, H2 behaving like a stuck at 0 because of the open may not impact H1 and H at all. Similarly, H1 may get short circuited with something, right, or it may become open, right, but the other part of the circuit is okay. Okay. So, that is the reason why we distinguish between H stuck at 0, H1 stuck at 0 and H2 stuck at 0. Similarly, we distinguish between H stuck at 1, H1 stuck at 1 and H2 stuck at 1. Okay. So, fan out stems and fan out stem. So, we had looked at fault compaction, right. What you have to remember is there is a sort of a theorem, okay, which says that it is enough to consider the faults or the single stuck at faults at the primary inputs and the fan out branches. So, this is the sort of fault compaction theorem that may be useful. Okay. I will not prove this, right, it is based on equivalence and dominance. Okay. Equivalence and dominance. So, you can start eliminating the faults, right, based on equivalence and dominance. Okay. So, let me, so if I rewrite the same circuit, we had called this guy A, B, C, D, H, H1, H2, E, F and G. So, let us use our fault compaction theorem. It says that it is enough to consider the stuck at faults at the primary inputs. So, the primary inputs are A, B, C, D. The fan out branches are H1 and H2. So, it is saying that it is enough to consider the stuck at 0 and the stuck at 1 here, stuck at 0 and stuck at 1 here, stuck at 0, stuck at 1, stuck at 0, stuck at 1, and then stuck at 0, stuck at 1, stuck at 0, stuck at 2. So, it boils down to about 12 vectors, 12 faults. Okay. Whereas I had earlier 2 plus 2, 4, 6, 8, 10, 12, 14, 16, 18 faults. So, from 18 it comes down to 12. Okay. We may be sometimes further reduce. See, for example, D and H2. Okay. So, there is an OR gate. So, H21 and D1 are same. So, if you are considering a H21, there is no need for D1. So, it may reduce one more fault. Similarly, H11 and A1 are same. So, I can drop 2 more faults. Okay. So, we can further drop maybe H11 and H21. Okay. So, this theorem it reduces quite a few faults, okay, but some more optimization may be possible. Okay. So, in our example we can bring it down to 10 faults. Okay. In fact, we can do little bit more. See, B0 and C0 are the same. So, it is enough. B0 can be dropped. If you are looking at C0, we can drop B0. So, we can bring it down to 9 faults. Okay. So, we started with 18 faults and we can go down to 9 faults. Okay. So, this is a useful technique, right? It reduces our effort.